So welcome back. Let's now continue with our fourth video about the variable elimination, and now let's turn our attention to compute some posterior marginals. So what's going to be different now is that we're going to set some evidence. So let's suppose that the evidence that I'm interested in is this evidence here. So I'm going to say that A is equal true and B equal false, and given this evidence, I want to compute the probability for the query variables D and E. For example, if we have this Bayesian network here, and we want to compute those posterior marginals for D and E, we will get this answer here. So this is going to be the probability of the query variables, that are D and E, given the evidence that is A equal true and B equal false. So in a more general way, if you have a Bayesian network N and the query variables Q and evidence E, we want to compute the posterior marginal, that is the probability of Q given A. Compared to what we have done before, that was computing the prior marginals, we can understand that the prior marginals that we had before is a sort of a special case of the posterior marginals when E is the trivial instantiation. But we're going to use a little trick here. So instead of computing those posterior marginals, we're going to compute something that's similar, that's called the joint marginals. That is the probability of the query and evidence. So for this Bayesian network here, the numbers are going to be slightly different because we are not computing the probability of query given evidence, but we are computing the probability of the query and the evidence. And we're going to get those numbers that are shown in this table here. But if we sum all those numbers together, we're going to get this 0.48, that is the probability of evidence. So basically what we are doing here is using the case analysis. So we know that if we sum all the probabilities of P given A together for all possible values of Q, I will get the P of E. So this is going to be the probability of the evidence. In this case, is the probability of having A equal true and B equal false. And because of the Bayes conditioning, we know that the probability of Q given E is equal to the probability of Q and E divided by the probability of E. If I have the probability of E, that is this 0.48, I can obtain the posterior marginals from the joint marginals that I have here, just by dividing everything by 0.48. So it's going to be like a normalization process. So we sum all those values here and divide each value by the sum, that is 0.48, and we get the posterior marginals. Okay, now great. Now everything that we need to know is how to compute those joint marginals in the presence of evidence, right? So we need to incorporate evidence before, and we have not done this before when we defined the previous algorithm for variable elimination, but we know that we can do that by eliminating every row that we have that do not match the evidence. Let's see how we do that in the next slide. And the process of incorporating evidence is actually very simple. What we do is we zero every row that do not match the evidence. We call this process the reduction. So we get a reduced factor from the original factor, and we denoted by this symbol here. This is not the one exponentiation, it's just an information that this factor matches the evidence that is contained in E. So by definition, what we have to do is to take each row and see if the row matches the evidence. So we're going to see if the instantiation that I have in a certain row of the factor, if it matches my evidence. If it does, I keep the number. If it doesn't, I just put 0 instead of the value of the probability that I have before. So let's suppose that we have this factor here, f, that it is defined over the variables D and E. And I have a piece of evidence that is E equal true, and I want to compute the reduced factor Fe. So basically what I'm going to do is to look at this factor and see the rows that do not match my evidence. In this case, the rows that we have E equal false, and I'm going to zero those rows. So in this case here, I will eliminate this row, and I'm going to eliminate this row here. So now I have this factor here in which the second and the fourth rows are 0. I can eliminate these. I don't need to represent them. I can have this reduced factor here in which we have only entries that match the evidence. In other words, entries in which the variable e is true. So for instance, let's suppose that we have this Bayesian network here that we are using as an example, and we want to compute the joint marginal that involves the query variables d and e and the evidence that is a equal true and b equal false. So it's going to be the probability of q and e. So a naive approach for doing this is to take the factors that compose this Bayesian network, joining them, so multiplying them together, and eliminate all the rows that do not match the evidence and do the summation. So we're going to eliminate the variables that we are not interested in. This case are the variables a, b, and c. But this approach is exponential in size because we need to multiply all the factors together, so you get a factor that has all the variables that we have in the network together, and it's going to be exponential in this number of variables. But we can use this result here. So basically what I'm saying is that instead of multiplying the factors, I'm going to move this evidence here to each of those factors. So I'm going to make the factors, all of them, compatible with the evidence first, and later on I can eliminate the variables. So I have this result here. And as we know, because I have this result, I can move this summation and do the variable elimination, so you're not needed to compute the full joint distribution. So again, it's very useful to use a very simple example so we can check if you are understanding the details. So let's suppose that we have this network here, just 3 variables, and our query is the variable c, and our evidence is a equal true. So the first thing that we needed to do is to make the network, all the factors, to match the evidence. So you eliminate everything that doesn't match the evidence. So a equal false is going to be removed from here, a equal false and a equal false being removed from here, and here I did not need to touch this because it doesn't mention variable a. All right, so after we do that, we can start enjoying the factors and eliminating the variables. In this case, we're going to eliminate the variable a first, and then we're going to eliminate the variable b. So now we have here, in a bit more organized way, the factors matching the evidence a equal true. So we need to eliminate the variable. So what we're going to do is to join the factors together, eliminate the variable a, and eliminate the variable b. But the factors that mention variable a are just these two here. So we're going to move them forward and do the elimination of a variable a first. That is the variable elimination algorithm. So we have these two factors that mention variable a. So we're going to join them together. We're going to have a new factor here that mentions variables a and b, and we're going to have the multiplication of them. So we're going to multiply for a true and b true. I'm going to take this row, if this row here, they match the assignment here, and going to be 0.6 times 0.9 equals to 0.54. All right, and I'm going to compute this guy here, that's a and not b, going to be a here and a and not b here, going to be 0.6 times 0.1, I'm going to have 0.06. All right, so ready to eliminate the variable a. So to eliminate the variable a here, what I have to do is to take the variable b and iterate over all possible values of the variable a, summing them all together. But we only have the a equal true, so that's fine. At the end, I will copy this value to here, and copy this value to here, and I have eliminated the variable a. Now I can get rid of these two factors here, and I will eliminate the variable b by just looking at this factor and this factor. These are the two factors that mention variable b. And I continue doing this process, and now I'm going to eliminate the variable b. And the variable b is mentioning these two factors, so I have to join them. So again, I will have a new factor that mentions variable b, and B and C. So I have it here, variables B and C. And for each entry here, I'm going to multiply the values. So having B true and C true, I'm going to multiply this guy here, 0.54, by B true and C true by 0.3. The result is 0.162. I will multiply for this entry here, B and so I have a B here, 0.54, and B and not C here, 0.7. The result is 0.378. And I continue doing that for all possible instantiations of B and C. When I have finished with that, I needed to eliminate the variable B. And so this is the variable B that I needed to remove. I will keep only the variable C. To do that is the summation process. I take for variable C, one value, and I iterate for all possible values of a variable B. So I have variable C true, and I sum these two values here, and I will have as result this value here. For variable C false, I will sum these two values here, and I have a result in this one. So now I have just one factor that mentions the variable C, and is this factor here. But be careful, because if you are interested in the probability of C given A equal true, I still do not have it. What I have right now is the probability of C, the probability of C and A equal true. I will have to normalize these results in order to get the conditional probability. Let's do this in the next slide. Great, so here a little bit more organized, I have this new factor that we just created that mentions variable C. So this is the guy, this is the probability of C and A equal true. I'm interested in this guy here, the probability of C given A equal true. So on the top one, I'm not sure if I said it correctly, it's the probability of C and A equal true. So what I have to do is to sum the two entries. Are going to be 0.600, and I divide each of the entry by this value. So let's call it Z. So I divided this by Z, and divided this other guy by Z, and I get these results here. So these are the probabilities that we were looking for. And we got for free the probability of A equal true. That is the probability of evidence, that is 0.6, right? That's good. Okay, so yeah, this is our final slide for computing those posterior marginals, and the algorithm is very similar to what we had before. So we call it the first algorithm the VE-PR1. This is the VE-PR2. It's the same thing. Basically, what we are doing is to set the evidence in the factors first and computing the variable elimination algorithm. So let's take a look. We have the variable, the Bayesian network N, we have the query variables Q, we have an elimination order pi, and we have now the evidence E. So we're going to compute the joint marginal, the probability of Q and E, right? And if you want, you can normalize later and get the probability of Q given E. What we have to do that's going to be different from the previous algorithm is just this line 1 here. So we set the set S to be all the factors that we have in the Bayesian network that match the evidence E. So we are represented by this symbol here. And everything continues to be the same. I'm going to iterate over all the variables in the elimination order according to the elimination order pi. And I will multiply all the factors together that mentions the variable pi I. And after joining those factors together in a single factor that we are calling F, I will eliminate the variable pi I by doing the summation process. I'm calling this new factor Fi. Now I eliminate all those factors Fk from S. These are the factors that mention the variable pi I, and I will introduce in S a new factor Fi that I just created. I iterate this process during the entire elimination order. When I get to the end of the elimination order, I will have a series of factors that mention the variables in Q. If I want to, I can multiply those factors together and return that to the user. Remember that it's going to be the probability of Q and E. If you want the probability of Q given E, you need to do a normalization process. So it's not uncommon to run this algorithm with an empty Q. So in this case, I will get as result a trivial factor with the probability of the evidence, and that is useful by itself in the case that we want to compute this probability. Alright, so I think that is good for this video, and we will continue in the next one, talking a little bit more about the efficiency of the variable elimination algorithm. See you soon.